Hello everyone, welcome to the 6th class of this course. In the past few classes, what we did is basically if we are given a second order differential equation and we are asked to find out a power series solution at an ordinary point, then how should we do? So two examples we showed, and so in this class what we will do is basically if we are given a second order differential equation and we are asked to find out a power series solution at a regular singular point, so then what should be the procedure? Okay, so the procedure is called the Frobenius method. So what we will do is basically let's say we are given a second order differential equation and we are asked to find out. So let's say we are given a second order differential equation and we are asked to find out a power series solution at a point let's say x equals to x0, where x0 is a regular singular point. For example, we already showed that if we are given a Bessel equation, in that case the x equals to 0 point will be a regular singular point. So there we will apply basically this Frobenius method to get the Bessel functions. Okay, so let me tell you what should we do if we are asked to find out such a power series solution. So then instead of assuming, so then we will assume, or we will start with so instead of starting with y equals to sum over n an x to the x minus x naught to the power n, what we will do is we will start with y equals to sum over an x to the power n x minus x naught to the power n plus s. Okay, so here this s is an unknown constant. Okay, so this s we have to determine along with ans. Okay, so here n equals to 0 to infinity. So this is the procedure we should follow. So let's look at some examples. So today I will solve one example, and in the next class I will solve another. So let's take example 1. Okay. So the given differential equation is x square d2y dx2, that is y double dash, plus 4x dy dx, that is y dash, plus x square plus 2 times y equals to 0. Okay. And we are asked to find out, so and find out a power series solution at x equals to 0. Okay, so x naught is 0. So this x naught is 0 for this problem, for this example 1. So let me first show that okay, x equals to 0 is indeed a regular singular point. It's not a not an ordinary point, it's not an essential singular point, it's a regular singular point. So for this case, this is our px, this is our qx, and this is our rx, right? So px qx by px. So what is qx? Qx is the 4x. 4x divided by x square equals to 4 by x, and rx divided by px, which is x square plus 2 divided by x square. Okay, so you can see at x equals to 0, both these ratios qx by px and rx by px both diverges. So it's basically at x equals to 0, at x equals to 0, none of them are analytic. So what conclusion we can draw from here? We can say that x equals to 0, so x equals to 0 is not an ordinary point. So we can't go with the usual method of assuming the solution as y equals to sum over a n x minus x naught whole to the power n. Okay, so now let's check whether x equals to 0 is a regular singular point. How to check that? Qx by px times x minus x naught. Here x naught is 0, so x minus x naught, which is basically x, and we know that qx by px is 4x times x, which is 4, right? So 4, and rx by px times x minus x naught whole square. Here x naught is 0, that means it is just x square. Okay, and rx by px is x square plus 2 divided by x square times this x square. Okay, and this x square cancels, so what we are left with is x square plus 2. Okay, and you can see that okay, at x equals to 0, both of these functions are analytic. These are all well-behaved functions. So at x equals to 0, at x equals to 0, analytic means the limit exists basically. So at x equals to 0, both are analytic. Okay, both means qx by px times x and rx by px times x square, both are analytic. It means, so x equals to 0 is a regular singular point, is a regular singular point for the given differential equation. Right, so we have to use the Frobenius method. And what is that? We have to assume that our yx is sum over n equals to 0 to infinity an x minus x naught to the power n plus s, and now we know that x naught is 0. We are trying to find out the series solution at 0. Okay, so our x naught is 0, so it means basically x to the power n plus s. So after that, what we do? We do so we basically calculate this y dash. We will calculate x y dash. We will calculate y double dash. We will calculate x square y double dash, and then we will put them after index shifting. Basically, we will put them in the differential equation, and then we will compare the coefficients corresponding to same power of x. So that's what I am going to do now. Okay. So let's look at this third term. So let's look at this term. What this term is saying? It is saying x, let me write it in blue. It is x square plus 2 times y. X square plus 2 times y, okay, equals to, so it will be then x square times y plus 2y. Good. And now x squares times y, which is basically n equals to 0 to infinity an x to the power n plus s plus 2, because there is x square sitting here, and the other term is 2 times sum over n equals to 0 to infinity an x to the power n plus s. Okay. So now instead of x to the power n, we have a n plus s. So for comparing the coefficients, we need to do index transfer, and we need to write these summations where there will be x to the power n plus s, not terms like x to the power n plus s plus 2. Okay, so this term is fine, we are good to go with this term, but here x has a power of n plus s plus 2. So we want to do the index shift, and we want to bring down the power, or we are not to bring down, we want to write the summation as, so sum over some coefficient times x to the power n plus s, so that we can compare. Okay, so that's the goal here. So we will leave this term. Okay, so this term we will leave, and we will only work with this term. Okay, so I'm leaving it as it is, and I'm working with this term. I'm working with this term. So what it says is basically we want n plus s plus 2 equals to so what we do is s is a constant, so and n is the summation index here. So what we need to do is basically we need to write n plus 2 as m, right? So if we are, so for n plus 2 we are writing it as m. So it implies n equals to m minus 2, and if n equals to 0, m equals to 2, right? Put n equals to 0, you will get m equals to 2, and if n tends to infinity, m also tends to infinity, right? So now we can manipulate this term. So here I am replacing n by m, so instead of n starting from 0, I will write m starting from 2, right? So m equals to 2 to infinity a m minus 2, right? Instead of n I am writing m minus 2, and x to the power m plus s, right? So n plus 2 I am writing as m, and as m is a summation index, I can write it as sum over n equals to 2 to infinity a n minus 2 x to the power n plus s. Okay, so basically what we have is this term, the third term of the differential equation, which is this one, this blue, indicated by this blue. So that is x square plus 2 times y, which is equals to sum over n equals to 2 to infinity a n minus 2 x to the power n plus s plus twice this term. Okay, this is I am keeping as it is, twice sum over a n x to the power n plus s, right? N equals to 0 to infinity. Now let's go for the second term. Okay, so now we're going for the second term. What's that? So for that we need to calculate y dash first. Y dash equals to ddx of y, and what is y? It is a n x to the power n plus s. Okay, n equals to 0 to infinity. So it is basically n equals to 0 to infinity n plus s a n x to the power n plus s minus 1. Okay, and now here we cannot, so zeroth term still exists here. Zeroth term will not vanish for this, series. So in previous cases where we are solving for ordinary points, so there we didn't have this s, so in that case the zeroth term will vanish because n equals to 0, but here we have this s, so it means that zeroth term will not vanish. Okay, so here we have to start the series from n equals to 0, and the term is basically 4x y dash. Okay, so if I now write 4x y dash, which equals to 4 sum over n equals to 0 to infinity n plus s a n x to the power n plus s, because there is one x multiplied with x dash, right? So this is the second term. Now let's look at the first term, which is, so now let's look at this first one, this term, which is x square y double dash. So for that we need to calculate y double dash first. Okay, let's calculate y double dash, which is ddx of this term. So that is n equals to 0 to infinity n plus s minus 1 a n x to the power n plus s minus 1, right? Sorry, minus 2. This series is, will also start from n equal to 0 because of this s. Okay, and the term is basically x square y double dash. So what we will do is we'll calculate x square y double dash equals to sum over n equals to 0 to infinity n plus s minus 1 a n x to the power n plus s, and x has a power of n plus s, so we don't need to do the index shifts, power is already matching. So now what we will do, we will put these terms together and in this differential equation. So let's write the first term, that is x square y double dash, and that is this term, okay. So this is n equals to 0 to infinity n plus s minus 1 a n x to the power n plus s. Fine. Now let's go for the second term, that is this one, which is 4 times, so plus, right? Yeah, it's plus 4 times sum over n equals to 0 to infinity this one, n plus s, this one, n plus s a n x to the power n plus s. So n plus s a n x to the power n plus s. And the third term has basically 2 terms, okay. Yeah, this one, so it has 2 terms, this one plus this one. So this term is n equals to 2 to infinity, so plus sum over n equals to 2 to infinity x to the power n plus s, a of n minus 2, let me check it again, n minus 2 x to the power n plus s, plus sum over n equals to 0 to infinity twice a n x to the power n plus n, s twice a n x to the power n plus s equals to 0. So now we will follow the usual method, okay. So that is, so this series, it is starting from, so all the series, they all have x, so for in all the series x is the power of n plus s, but we still cannot put them together because this series, it is starting from n equals to 2, and all other series, they are starting from n equals to 0, okay. So we need to do something so that all the series are starting from the same number. So to do that, what we will do is, we will try to start all the series from n equals to 2, okay. Instead of that, I can put these 3 terms together, okay, because for these 3 terms, all are starting from n equals to 0, and all have x as a, all in all the terms, x has a power of n plus s, okay. So that's what I will do now in the next line. So n equals to 0 to infinity n plus s times n plus s minus 1 a n, okay. All these terms, in all these terms, a n is common, a n and x to the power n plus s is common, so I can write it outside, okay. So plus 4 n plus s plus 2, okay, times a n x to the power n plus s, plus this term, okay, that is sum over n equals to 2 to infinity a of n minus 2 x to the power n plus s equals to 0, okay. Implies, so if I do this summation, let me do the summation. So I can take n plus s common, n plus s, if from these 2 terms, this term and this term, okay. So then we are left with n plus s minus 1 plus 4. Plus 4 means this plus 3. Plus 2. Okay. Sorry, let me write in green. So n plus s plus 3 plus 2. So then I can write it as sum over n equals to 0 to infinity n plus s plus 3 n plus s plus 3 plus 2 times a n x to the power n plus s plus a n minus 2 x to the power n plus s equals to 0. Okay, here n is starting from 2 to infinity. So now what we will do, we already did this kind of problems, or this kind of tricks basically. So I will write, so this series it is starting from n equals to 0. So what I will do is basically I will write the 0th term and the first n equals to 1 term separately, and then I will write the rest of the series, which will be starting from n equals to 2. Okay, so the 0th term is basically I will put n equals to 0, and we will get s times s plus 3 plus 2 times a0 plus n equals to 1. If I put, then I will get 1 plus s 1 plus s plus 3, that is s plus 4. Okay, that is s plus 4 plus 2 times a1 x to the power 1, sorry, this is x to the power s, and this is x to the power 1 plus s. Okay, plus sum over n equals to 2 to infinity. So this term is n equals to 0th term. Okay, so if I put n equals to 0, then you see it will be a0 and it will be x to the power s, and this is n equals to 1th term. So if I put n equals to 1, this will be a1 and this will be x to the power n plus s plus 1. So that's what I wrote here. Okay, and then all the other terms, that means it will start from n equals to 2, n plus s plus 3 plus 2 times a n x to the power n plus s plus. So these are the lengthy problems. I will ask you to do, do it along with me. In that case it will not be boring. Good. So now we can put these two terms together. That's what we will do. Okay, so now this term I can write it as s square plus 3s plus 2, s square plus 3s plus 2 times a0 x to the power s, right, plus this term. So this I can write as s square. So if I multiply them, then what we will get? We will get s square plus, so this 4 is multiplied with this s, there will be 4s and there will be 1s here. So 4s and 1s, that is 5s. So it will be 5s plus 4, and there is plus 2 sitting here, so it will be s square plus 5s plus 6 a1 x to the power s plus 1, right? Good. So, and these two terms, okay, these two terms, this term and this term, we will put them together, plus n equals to 2 to infinity n plus s times n plus s plus 3 plus 2 an plus an minus 2 x to the power n plus s, you can take that common, equals to 0. Okay, and let's make the coefficients 0. Okay, so we will make this equals to 0, we will make this equals to 0, and we will make this equals to 0. So first make this equals to 0, the coefficient of x to the power s. So if I do that, then plus 3s plus 2 equals to 0. Okay, so times a0, sorry, times a0 equals to 0. Okay, so for the time being I am assuming, okay, a0 not is equals to 0, right? So in that case what we have is basically s square plus 3s plus 2 equals to 0, and it implies s plus 2 s plus 1 equals to 0, which implies s can take two values for which this equation will satisfy, like it will be 0, that is minus 1, either minus 1 or minus 2. Good. So these are the two values s can take. Here we have assumed that a0 not is equals to 0. Okay, and now let's look at this equation. Okay, so I need to make this also 0, right? So if I make this term equals to 0, so I will do that here. That is coefficient of x to the power s plus 1. Okay, so that is s square plus 5s plus 6 times a1 equals to 0. So now we know that s equals to minus 1 and minus 2, right? So let's put s equals to minus 1. If s equals to minus 1, you see what's the value of this term. So if I put s equals to minus 1, in that case this term will be 1 minus 5 plus 6, which is 2. 1 minus 5 plus 6 is 2, right? So this term is not equals to 0. That means it implies a1 must be 0. Otherwise s we cannot take these two values. So it basically says that, okay, if s is taking these two values, and that is because of we have assumed that a0 not equals to 0. So in that case a1 must be 0. Okay, so if a0 not equals to 0, s will be taking minus 1 and minus 2, and a1 will be equals to 0. You can do it in a different way, like you can take, I mean you can try it yourself, that you can take it as homework, right? Like you can take a0 not is equals to 0, and in that case you will see it will give you, so you can take a1 not is equals to 0. Okay, so you can start with a1 not is equals to 0, and in that case you have to make this term equals to 0. So this term equals to 0, and this will give you two values of s, right? This will give you two values of x. Let me tell you, it will be minus 2 and minus 3, and for minus 3 you will see a0 will not be will have to be equals to 0, because for minus 3 you will see this term will not be equals to 0. So a0 you must take in that case it 0. Okay, and you will get the same solution. You can try to do it yourself, you know, you can follow now, and after that you will follow the same procedure as I will follow for this case, and you will get the same solution. Okay, so for this case means a0 not is equals to 0, a0 not is equals to 0, s equals to -1 and -2, and a1 equals to 0. Okay, so let's first check for s equals to -1, right? So if s equals to -1, then let me write this equation. Okay, so this term is also 0, we will make this term will also 0. So in that case, okay, let me write it without s equals to -1, let me write it with s. Okay, so okay, so this coefficient if I make 0, so then for n greater than equals to 2, sorry, greater than equals to 2, we have this term, okay, this term equals to 0. So basically we have n plus s times n plus s plus 3 plus 2 a n plus a n minus 2 equals to 0. That's what we have, right? And it basically says that, okay, then a n equals to minus a n minus 2 divided by n plus s times n plus s plus 3 plus 2. So this is our recursion relation or recurrence relation. This is our recurrence relation. Right? So if we are given n minus 2th term, we can find out nth term. That's the meaning of this recurrence relation. And let's put s equals to -1 here, because first we will investigate s equals to -1. So if I put s equals to -1, right, so then what this recurrence relation will say, it will say, okay, a n equals to minus a n 2 divided by n minus 1 times n plus 2 right? So now we will start from a0 because a1 is already so a1 is already 0. We showed that, okay, if s takes these two values, or if we start with a0 not equals to 0, if we start with a0 not equals to 0, a1 is 0, a1 have to be 0. So we will start with a0. So we'll start with a0. Okay, and what this recurrence relation tells us, it tells us that I can, so from a0 I can find out a2 basically. So if I put n equals to 2, so we have a1 equals to 0. Okay, we have a1 equals to 0. So if I put n equals to 2 in this recurrence relation, then what we have is basically a2. So what this recurrence relation tells us is basically a0, a1, a2, a3, a4 dot. Okay, and if we know a0, we can find a2. If we know a2, we can find a3. Okay, similarly, if we know a1, we can find a3. If we know a3, we can find a5. But a1 is 0, right? A1 is 0, and a3 will be so in expression of a3 there will be a1 multiplied with it, so that means a3 will also be 0. Similarly a5 will also be 0, so we will not bother about that series. So we'll only interested in a0, a2, a4, these terms, even terms, even indexed terms. So a2 will be, from this recurrence relation, it will be minus a0, because a n minus 2, that is a0, and so for n equals to 2, so it is n minus, so 2 minus 1, that is 1, right, times 2 plus 2, that is 4, so it is 4 plus 2, which is 6, so it will be minus a0 by 6, or I can write it as 2 times 3, or I can write it as 3 factorial, right? Okay, so let me write here, if I put n equals to 3, in that case we will get, from this recurrence relation we will get a3 equals to minus of a1 divided by something, but a1 is 0, that means a3 will also be 0. Similarly all the other odd index terms will be 0. Okay, now put n equals to okay, I can also modify this recurrence relation a little bit, that will be useful, I think. Yeah, okay, I don't have space here, let me write it here. So it will be minus a of n minus 2, okay, and n minus 1 times n plus 2, if I do the multiplication it will be n square, there will be minus n, there will be plus 2n, so that will be just n, so plus n minus 2, and there is here there is plus 2, so this 2 cancels and we are left with, if I take n common, then it will be n plus 1, so it will be n times n plus 1. Okay, so it will be n times n plus 1, right? This is our recurrence relation. This is our recurrence relation. This is our recurrence relation. It is becoming a little bit messy, but okay, good. So, and I can, you can see that, okay, if I put n equals to 2 here, you will automatically get 2 times 3, there is 3 factorial. Okay, you don't need to do the calculations. If I put now n equals to 4, I will get a4 equals to minus of, so 4 minus 2, that is a2. I am following the recurrence relation. Okay, and 4 times 5, and we know that, okay, a2 is minus of a0 by 3 factorial, and if I put the value it will be plus, then there is a minus here sitting and there is a minus here sitting, so it will be plus 1 by 3 factorial times 5, 4 times 5, that means it will be 5 factorial, 5 factorial a0. Okay, great. And this, a5 will be 0 if I put n equals to 5. So similarly, if I put n equals to 6, it will be a6 equals to minus of a4 divided by 5 times it will be 6 times 7. Okay, so n times n plus 1, so it will be n equals to 6, so it will be 6 times 7. And what is a4? a4 is a0 by 5 factorial, So we are left with a0 by 5 factorial times 6 times 7, that is 7 factorial. Okay, and it will proceed like this. So the series what we have basically, if we have s equals to -1, the series we have basically, so I can write it as y s for s equals to -1 is a0 x to the power s plus a1 x to the power, let me write the summation sign. So sum over an x to the power n plus s, n equals to 0 to infinity. Good. And the first term will be then n, for n equals to 0 it will be a0 x to the power s plus a1 x to the power 1 plus s plus a2 x to the power 2 plus s plus a3 x to the power 3 plus s plus a4 x to the power 4 plus s plus dot dot dot. Okay, and we know that okay, a1 equals to 0 and a3 equals to 0, and all the odd indexed terms are 0. So that means a5, a7, those all are 0. So that means we are left with y s equals to -1 equals to okay, so s is -1, right? So s is -1. So a0 x to the power -1 plus a2 is minus a0 by 3 factorial. Okay, so a2 is minus a0 by 3 factorial, and 2 plus s, and s is -1, so it is x plus a4. What is a4? a4 is a0 by 5 factorial, so it is a0 by 5 factorial times x to the power 4 minus 3, that is 4 minus 1, it is 3 plus, okay, minus what is a, so for after a4 there will be a6. So what is a6? a6 is minus a0 by 7 factorial, it is minus a0 by 7 factorial, and x to the power 6 plus s, that is 6 minus 1, that is 5. Okay, plus dot dot dot, and I can take a0 common, I can take a0 outside, and I can also take x to the power -2 outside, and y -2, you will notice, you will just understand. So the series will be then x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial plus dot dot dot, right? So if I multiply x to the power -2 here, you will get this minus x to the -1. If I multiply it here, you will get x. If I multiply it with x to the -2, if I multiply x to the power 5, you will get x to the power 3. So this step is correct. Okay, so now if you look at this series, I think this might seem I mean, it might look familiar. This is a series of sin x, it's a Maclaurin series, sin x at x equals to 0. Okay, so you can see there are these odd terms basically, because sin x is an odd function, so there it consists of odd powers of x. Okay, so what we have is basically a0 sin x divided by x square. So this is for s equals to -1. Okay, this is the solution when s equals to -1. And let's look at the other value of s, that is for s equals to minus, so minus 2. Okay, so s equals to minus 2. Because the idea is very simple. It's a second order differential equation, so we are expecting two independent solutions. So one we got for s equals to minus 1, and other we will we will find for s equals to minus 2, and then the general solution will be a linear combination of these two solutions. Okay, for s equals to minus 2, let me write down the recurrence relation. So the recurrence relation was an equals to minus of an minus 2 n plus s times n plus s plus 3 plus 2, n plus s plus 3 plus 2. Okay, and if I put s equals to minus 2 here, then it will be minus 2 here, it will be minus 2 here, and it will be minus 2 here, minus 2 here, and I can write this term as n plus 1, right? So I will write this term as n plus 1, n plus 1. Okay, and also I can simplify it, so I can multiply these two terms. It will be n square minus 2n plus n minus 2. Okay, and there is plus 2 sitting here, so these two and these two will cancel, and we are left with, so we are left with then n square minus n, which is nothing but n times n minus 1, right? So what we have basically is, I can simplify this term as then minus an minus 2 divided by n times n minus 1. This is now a recurrence relation for s equals to minus 2, right? And we will start from a0. Obviously here also we will start from a0, because we know a1 equals to 0, and this recurrence relation tells us that okay, all the odd index terms are 0. So we will start with a0 and we will get a2, a4, a6, these terms. Okay, so now if I put n equals to, okay, and this recurrence relation is valid, so it's because this summation term, it is starting from n equals to 2, and the recurrence relation we got here, it is from that this coefficient of this summation term. So this recurrence relation is valid for n greater than equals to 2, right? N equals to 2 and higher values of n. So I will start with n equals to 2 then. If I start with n equals to 2, so then what this recurrence relation is telling me, it is telling me a2 equals to minus a0 divided by n times n minus 1, that is 2 times 2 minus 1 is 1, so 2 times 1, that is 2 factorial. So it is 2 factorial. Good. Now here in this side I can write is a1 equals to 0. Okay, and if I put n equals to 3, then I will get a3 in terms of minus a1 divided by something, there will be some non-zero thing, and a1 equals to 0 I know already, so a3 will also be 0. For other n equals to 5, n equals to a5 will be 0. For n equals to 7, a7 will be 0, and so on. Okay, in this side let me put n equals to 4. In that case, what the recurrence relation will give me, it will give me a4 equals to minus of a2, okay, an minus 2, that is n equals to 4, so it will be a2 divided by, so n equals to 4, so it is 4 times 3, n minus 1 is 3, so it is 4 times 3, right? And a2 is nothing but minus a0 by 2 factorial. Okay, so if I put it then minus minus, it will be plus, so So it will be plus a0 divided by 2 factorial times 4 times 3, that is 4 factorial. Okay, now if I put n equals to 6, so then it will be a6 equals to minus a4 divided by, so n equals to 6, and this recurrence relation tells you that it will be, so a4 n minus 2, that is 4, it will be in the denominator it will be 6 times 5, right, n times n minus 1, that is 6 times 5, so it will be 6 times 5, and we know that a4 is a0 by 4 factorial. Okay, so then it will be minus a0 by 6 factorial, and so on and so on. So for y equals to for s equals to minus 2, the series will be sum over n equals to 0 to infinity a n x to the power n plus s. Okay, and s is minus 2, so it is n minus 2, right, and it will be, then series will be then a0 x to the power minus 2 plus a1, sorry, a1 is 0, right, so I am not writing these terms, plus a2 x to the power 2 minus 2, that is 0, right, or let me write it 2 minus 2, 2 minus 2 plus a4 x to the power 4 minus 2 plus a6 x to the power 6 minus 2 plus dot dot dot, all the even indexed terms. Okay, now it will be a0, I can take x to the power minus 2 common, or let me keep it as it is. Okay, let me keep it. What is a2? a2 is minus a0 by 2 factorial, it will be minus a0 by 2 factorial x to the power 2 minus 2 plus a4, a4 is a0 by 4 factorial, so it is a0 by 4 factorial x to the power 4 minus 2 minus a6 is minus of a0 by 6 factorial, it is minus a0 by 6 factorial times x to the power 6 minus 2 plus dot dot dot. So now you know, now we can see okay, what terms we should take common so that I can get a well-known series, and what series it will be. So there are terms like 2 factorial, there will be alternative, there are alternative plus minus terms, and there are things like 2 factorial, 4 factorial, 6 factorial. So we are expecting a cos series, basically we are expecting a Maclaurin series of cos function, cos x. So I can, so for that I need to take x to the power minus a0 x to the power minus 2 common. So then what I will get is basically 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial plus dot dot dot. Okay, so this is nothing but cos x. You can see all the even power terms are there because cos x is an even function, and so what we have basically, the solution, the power series solution for s equals to minus 2 is a0 x to the power minus 2 times cos x, or a0 cos x divided by x square. Okay, so these are the two series, and the solution, so the general solution will be, the general solution is yx which will be alpha y is equals to -1 x plus beta y is equals to -2x. So we got two independent solutions. So why I'm calling it two independent solutions, I will show you that this cos x and sin x. So we found that okay, y equals, so for s equals to -1 the solution is in terms of sin x, you know, and for this s equals to -2 it is in terms of cos x, and I will show you that okay, cos x and sin x, these two are linearly independent, or rather they are orthogonal basically. So we have I mean we already know that okay, what do you mean by orthogonality in case of vectors, where vectors I mean by vectors I want to mean Cartesian vectors, like which have magnitude and directions. But these kind of solutions, these are also, you will see that these are also vectors, and you know, these are vectors in some abstract notation or abstract algebra basically. So these two words, in these two, cos x and sin x, these are orthogonal vectors in function space, or these are linearly independent. So we got two linearly independent solutions, and the general solution will be the linear combination of them. So just like in case of, you know, Cartesian vectors, we got two, if we got two linearly independent vectors, for example, let's say two perpendicular vectors I hat and j hat, and in terms of I hat and j hat I can write any vector in the two-dimensional space, that is alpha I hat plus beta j hat. Same idea is, I mean the same kind of thing I'm doing here, like we have got two independent solutions, one this one, another is this one, and the general solution will be linear combination of these two solutions. So these are like I'm getting so this is like a solution space, you know, you can think of like a solution space, and I got two independent vectors in the solution space, and I am writing the general solution that can be, so solution space means all the solutions are lying there, and I'm getting two independent solutions, and I'm writing a general solution, so it will contain all the solutions depending on the value of alpha and beta. Okay, so I will motivate you to think in terms of this way. If you are not understanding what I'm saying, just bear with me, you will understand as you know, I will show you much more and more examples, but try to think in terms of this language, you know, this abstract notation. Think about vectors not just in terms of length and magnitude. Try to think of them in terms of some abstract notations. Okay, so general solution is basically this, and which is sin x by x square. So it is alpha a0 sin x by x square plus beta a0 cos x by x square, and I can write it as a, or let me write it as alpha 1 and or alpha tilde, and let me write it as beta tilde. Okay, so the general solution will be yx equal to alpha tilde sin x by x square plus beta tilde cos x by x square. Okay, so let me tell it again, repeat it once again. So these two terms, sin x by x square and cos x by x square, is similar, like, you know, in two-dimensional space I hat and j hat. And if I got I hat and j hat, to get all the vectors in this 2D, I will simply write alpha I hat plus beta j hat. Sorry, alpha I hat plus beta j hat. So with these two linearly independent vectors, or rather orthonormal vectors, I can write any vectors in the two-dimensional space. Similarly, these two terms are like two linearly independent solutions. Okay, and here instead of, you know, two-dimensional vector space, we have a space of solutions. Basically, you can call it a solution space. and here I mean all the solutions are lying here, and we got two independent solutions, and we are writing a general solution. So any solution will look like this, you know, like alpha, just like alpha I hat plus beta j hat. So if you want to know these kind of language much more rigorously, you need to do a course in linear algebra. Okay, but for this course I will I mean that is not needed. You can still find out solutions. Okay, so that's one example for today. In the next class I will solve another problem, and I will take another differential equation and try to find out the series solution at regular singular point, okay, using this Frobenius method. So this method is called the Frobenius method. Okay, so for the time being what you can do is, okay, you can check that here we started with a0 not is equals to 0, and that immediately leads to the fact that, okay, for that case a1 equals to 0. So you can start with a1 not is equals to 0, and you will see, okay, if a1 not is equals to 0 we need to satisfy, so then we need to put a0 equals to 0. Okay, and then we will follow the same method. You will get two values of s, and you will get the recurrence relation. You will put the value of s, and you will get two independent solutions, and you will see that, okay, you are getting the same solution. Okay, you're getting the same solution. So do it yourself. I think it will not be difficult. It will be similar to this treatment. Okay, so that's all for today. Bye.